In 10.8, we are going to graph polar equations. Before we get to the ones that are included in this section, I'm going to do example 0, which you don't have to copy, to kind of give you an idea of some of the basic types of graphs that can be easily graphed with a polar equation. So the first one is r equals 3. I'm going to think about it and graph it that way. I'm not going to make a table, although I could. So if I do theta comma r, say if I do theta equals 0, I'm along this line. If I go out 3 units, 1, 2, 3, I end up with a point around here. I could pick another point. What is this? Pi over 6. Pi over 6, the r is still 3, which would still put me out here. If I go to, say, pi over 2 is up here, 3 units, 1, 2, 3 is up here. And if I keep going around, I keep going out 3 units, which is going to create this nice little circle. And that seems like it should be right because it says r equals 3, so it's saying a radius of 3. So I created a circle with a radius of 3. One interesting thing to note is that the graphs of polar equations don't have a unique equation. So if I had called this instead r equals -3, that would have created the same graph. Because if I went along this line, but I went -3 units, I would be back here, which is on the same graph. If I went up to pi over 2, but I went -3 units, I would be down here, which is on the same circle. So r equals 3 and r equals -3 actually represent the exact same graph. Okay, let me look at the next kind of basic equation. It says theta equals 5 pi over 6. Let me find 5 pi over 6. 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6 is up here. I don't know what r is, which means if I went 5 pi over 6 and I went radius 0, I could be here. Radius 1 would be here. Radius 2.5 would be here. Radius -3, -1, 2, 3 would be back here. So my graph is going to lie everywhere along the theta equals 5 pi over 6 line because the radius can vary depending on the situation and it doesn't specify. Now again, this is not a unique equation for this graph. I could also call this, what is this? This is negative pi over 6. I could call it theta equals negative pi over 6. I could call it theta equals 11 pi over 6. I could call it theta equals -7 pi over 6, and it would all result in the same kind of graph. Okay, now in this section, we're going to explore certain kinds of special polar graphs, where once you get used to them, you'll recognize the shape, and then we will use symmetry to graph the function a little bit quicker than we might otherwise. So in terms of symmetry, which we'll play with Desmos in class little so you can see what I'm talking about, if your equation starts with r equals and it's in terms of cosine, so for example, r equals 4 cosine theta, it's symmetric with respect to the polar axis. The polar axis occurs where theta equals 0. So think it's like the horizontal axis. Okay, which tells me that if I knew what this half of the graph looked like, this bottom half would match. And I would use that as a hint to figure out how to graph this more efficiently. For r equals a function in terms of sine theta, it's symmetric with respect to theta equals pi over 2 line, which is this line. So it's symmetric to the vertical axis. And if you remember arc cosine and arc sine, this is consistent with that. It's also consistent with the unit circle. So we're going to use a table to graph some of the points, and then we're going to use symmetry to either check that our answers are correct or to get to our graph faster. Okay, so for the first one, it's r equals 4 cosine theta. Because it's in terms of cosine, it's going to be symmetric to the horizontal axis, or theta equals 0. So I normally like to start by plugging in theta equals 0, and then I'll work my way around the circle. And again, once we get better at these, we will be more efficient at plugging in less points. So if I plug in 0 4 times the cosine of 0, the cosine of 0 is 1. I get 4. So along theta equals 0, 1, 2, 3, 4. I have a point right here. Okay, let me plug in, let's try pi over 6. Pi over 6 would be right here. Okay, 4 times the cosine of pi over 6. The cosine of pi over 6 is root 3 over 2, which simplifies to 2 root 3, which I don't really want to graph, so I'm going to see if I can do it without that point. Eventually, you'll just include points that are easier to graph because it's easier for you. Okay, if I do pi over 3, The cosine of pi over 3 is 1/2. 4 times 1/2 is 2. So where's pi over 3? This is pi over 6, 2 pi over 6, 4. So this is pi over 3 line up here. R is 2, so 1, 2 is going to be up here. Okay, let's see. Let me plug in pi over 2. Cosine of pi over 2 is 0. 4 times 0 is 0. So at pi over 2, I'm at 0. Okay, now I'm going to plug in some more points because this is our first time graphing it. If we had graphed this before, though, I would use symmetry and what I know about the graph to consider the rest. Okay, now am I going to plug in what comes next after pi over 2? 2 pi over 3. Let me try 2 pi over 3. The cosine of 2 pi over 3 is negative 1/2. So I get negative 2. So along the 2 pi over 3 line, I go negative 2, which takes me back to here. Okay, what would I plug in next? Probably 5 pi over 6. But I don't want to do the pi over 6 because I get an ugly answer. So let me go back to pi. Cosine of pi is negative 1. So pi negative 4. So along the pi line, I'm going to go negative 4 units, 1, 2, 3, 4, which takes me back to here. Okay, so I'm going to go ahead and sketch this. I will tell you the hint that this is a circle. So try to make it look roundish. Now, when you get used to this and you noted that it's a circle, I could have graphed it using just probably these 3 points. And then because of this symmetry, I would have known that this point had to match this point. And I could have gotten the second half of the graph that way. Okay, so that's just to give you a hint of what it's going to look like. Let's do r equals 6 sine theta. I'll think about the symmetry as I'm going. And because I kind of know what it's going to look like, it's going to help me graph it faster. Okay, because this is in terms of sine theta, it's going to be symmetric to the theta equals pi over 2 line. So I'm actually going to start plugging in at pi over 2. You don't have to, but it makes it more efficient and easier to read my graph. So if I do 6 times the sine of pi over 2, the sine of pi over 2 is 1. So at pi over 2, I'm going to go 6, which is way over here. Okay, now I either need to do the right side or the left side. I'm going to go down the right side so I can get half of the graph done nicely. There's no reason I couldn't just use the left side though. Okay, if I go down the right side, this is pi over 2, this is pi over 3. I'm going to go ahead and plug in pi over 3 because it's just the next nice point. The sine of pi over 3 is root 3 over 2, which is 3 root 3, which I could estimate, but I'm going to just not use it. Let me keep going. I'm going to go down to pi over 6. The sine of pi over 6 is 1/2. So I'm going to get 3. Okay, now let me keep going down to here. This is 0. Okay, the sine of 0 is 0. So this is going to go right here. Okay, now weirdly enough, because of symmetry, I actually have enough points. If I'm not sure, I can always plug in another point. So let me see. If I keep going down here, I'm going to plug in this point. I'm going to call it negative pi over 6. You could call it 11 pi over 6 because it's the exact same point. The sine of negative pi over 6 is negative 1/2. So it takes me down to negative 3. So along negative pi over 6, I'm going to go negative 3, which is 1, 2, 3, which is up here. Okay, now the reason I could have skipped that point is because this is, in terms of sine, it is symmetric to the theta equals pi over 2 line, which means this point on the right had to have a match over here on the left. So I could have also just added that point and used the 3 good points I had. This should be a circle, so I'm going to sketch in my circle. Try to make it look round, even though you don't have all the points. Okay, so that's going to be a circle, and when it's of that format, it will always make a circle, and the symmetry will depend on whether it's in terms of cosine or in terms of sine. Okay, the next type of graph we are going to graph is called a limison. It's similar to the previous type of graph, except for it's going to be r equals a plus or minus b cosine theta, and this will maintain the symmetry to a, the theta equals 0 line. R equals a plus or minus b sine theta, and that will maintain the symmetry of the theta equals pi over 2 line. But this little constant added or subtracted at the beginning is going to change the shape of the graph. Once we graph it, you'll see that this is true. You don't need to memorize this, but this is what's going to happen. If this equals to this, there's going to be a little dimple at the pole, and you'll see it when I show it to you. If this is less than this absolute value, then it makes like an inner loop. But we're just going to make the table, we're going to go with it, and then use symmetry to figure out what it's going to look like. Okay, so this is r equals 3 plus 2 cosine theta. Because it's cosine theta, it's going to be symmetric to theta equals 0. So when I do a table, I start with 0. If I plug in 0, it's going to be 3 plus 2 times the cosine of 0, which is 1. So 3 plus 2 is 5. So my first point is out here. Okay, now let me think. Pi over 6, 3 plus 2 times the cosine of pi over 6 is root 3 over 2. And there's nothing wrong with this point, but I just don't want to use it because it's inconvenient. So what was that? That was pi over 6. Let me skip to pi over 3 now. And again, I only skip pi over 6 because it's not going to have a nice answer. Okay, the cosine of pi over 3 is 1/2. So 3 plus 1 is 4. Let me go to pi over 2. The cosine of pi over 2 is 0. Okay, I'm going to keep going because I want to go from 0 to pi if possible. Okay, let me go after pi over 2. Let's go to 2 pi over 3. The cosine of 2 pi over 3 is negative 1/2. So 3 minus 1 is 2, which is right here. What's next? There's a 5 pi over 6. I'm going to skip it because it's going to give me the root 3 over 2 thing that I don't feel like estimating. 3 plus 2 times the cosine of pi. The cosine of pi is negative 1. 3 minus 2 is 1. So that puts me here. Okay, now this is half of my graph. I'll go ahead and sketch in half of my graph. Okay, I could keep plugging in points, but because of the symmetry, I could also start matching up the points and graph it that way. So for example, I have to keep continuing. This is going to go like this. This point, this 2 pi over 3 is 1, 2 units. So if I go the pi over 3 line, it's going to go 2 units. Okay, at pi over 2, 1, 2, 3 units. So down here at negative pi over 2, 1, 2, 3 units. I'm matching it up so I can do the other half. Okay, let's see, at pi over 3, 1, 2, 3, 4 units. So on this line down here, 1, 2, 3, 4 units. And it should look like it's matching. And then I should go back to here. Let me sketch this in and see if it looks symmetric. Okay, so this is the shape of the graph. It's a limicone. I've seen limicone. We're going to go with limicone because that's what Google told me. Okay, it is symmetric to the theta equals 0 line. See, this is congruent to this. It's reflective. It has what they call a dimple right here, kind of goes in. So that's what they're referring to when they say dimple. You can use this fact to kind of like remember it, but normally if you use the table, you're going to discover it on your own anyhow. Okay, let's do another cosine one so you can kind of see the different options here. Okay, so this is r equals 3 minus 3 cosine theta. First thing I'm going to do is look at it. It's a cosine theta, so it's going to be symmetric to theta equals 0. So I'm going to start with 0 and plug in through pi so I can get half of the graph done nicely. The cosine of 0 is 1. Okay, let's see. The cosine of pi over 6 is root 3 over 2. So I'm going to skip it and go to pi over 3 just because it's more convenient. The cosine of pi over 3 is 1/2. So 3 minus 3 halves is 3 halves or 1.5 or something like that. About here. Okay, let me go up to pi over 2. Cosine of pi over 2 is 0. Okay, let me keep going around. This is 2 pi over 3. Cosine of negative 2 pi over 3 is negative 1/2. So 3 plus 1.5 is 4.5. You could decimal, whatever is convenient for you to do in your head. Okay, let's see. 5 pi over 6. I'm going to skip it because of that root 3 over 2 situation. Go to pi. 3 plus 3 is 6. So at pi, 1, 2, 3, 4, 5, 6. Okay, now again, remember this is half of my graph, but I know it's symmetric across theta equals 0. I'm going to go ahead and sketch this in, and that's just because I don't want to lose the order on my points. Okay, now I'm going to go ahead and sketch the other half of the graph, and it should be symmetric along the theta equals 0 line. So let's see, at pi over 3, 1, 2, pi over 3, 1, 2. At pi over 2, 1, 2, 3. Oh, that wasn't a 2, that was a 1.5. At 2 pi over 3, I did 4.5, so 2 pi over 3. And then if I go back to pi, I should be at 6. Okay, let me see. Does that look like it's symmetric? Let me draw it and check. Okay, it does look symmetric across the theta equals 0 line, which makes sense because it's in terms of cosine. Okay, let's do one more limosone. This one's going to have an inner loop, and also it's going to be sine, so you can remember that when it's sine, you want to use a different strategy when you plug in the points. Okay, because this is in terms of sine, it's going to be symmetric on theta equals pi over 2. So I want to plug in, I'm going to start with pi over 2. You don't have to, but it helps me remember where to start and to go down. I'm going to go down the right side. You could go down the left side. I'm right-handed. Okay, 2 plus 4 times the sine of pi over 2, 6. Okay, let's try pi over, what is this? Pi over 3 is over here. 2 plus 4 times, is that the root 3 over 2? There's nothing wrong with this. I just don't want to have to estimate it, so I'm going to skip it. I'm going to go to pi over 6. And if I don't need it, then I'll make my life a little easier. Let's go down to 0. Okay, I'm going to keep going down. If I go down to here, I'm going to call it negative pi over 6. You could call it something else, 11 pi over 6. It's the same value, no matter what I call it. The sign there is negative 1/2. So 2 minus 2 is 0. Okay, let's see. Negative pi over 3. I'm going to skip because of that root 3 over 2 stuff, but let me go to negative pi over 2. The sign is negative 1, so I'm going to get negative 2. So along the theta equals negative pi over 2 line, I want to go negative 2 units, which means I'm going to go back 2 units. Okay, now this is going to look a little strange. So I'm going to draw this and I'm going to do the other half. And you are going to want to draw it before you do the other half so you can keep track. You do need to go in order. So I started with pi over 2. Then I went to pi over 6. Then I went to 0. Then I went to negative pi over 6. Then I went to negative pi over 2. Okay, so this is half of my graph. I have to do the other half of my graph, and this is symmetric along theta equals pi over 2. This is going to have an inner loop. Okay, so let me think about this. This is going to go here. Let me see if I do the pi over 6, that was at 4 units. So let me go over here and draw him in. Okay, no, then what happened? It went down to here. So let me match this over to here. How are we looking so far? Okay, and then what happened? And then we went to the middle. And then we did this little loopy loop here. Okay, so if I look at it, it is symmetric across theta equals pi over 2. This little thing went like this, so it had to loop across the other side and went back like that. I really only needed 1, 2, 3, 4, 5 points to figure that out. If you really don't like matching it over, you could keep plugging in points. I could then plug in this point, this point, this point, this point, and I'll get the same graph. It just takes a little bit longer, and you have to be really careful to make sure you're going in order. Because this number was, absolute value of this was smaller than this, that's why you ended up with an inner loop. So if it helps you to remember that fact, you can use that. If not, you can just use your table. And as long as you're matching your table, you're going to find any inner loops or dimples anyways.